This is a video from section 12.5 and it's based off the lecture notes. Let's take a look at the directions. Determine whether the planes are parallel, perpendicular, or neither. If neither, find the angle between the planes. Let's take a look at 8a. Suppose we are given the planes negative x plus 4y minus 2z equals 0 and 3x minus 12y plus 6z equals 1. Now, we want to look at the normal vectors for each of the planes. Now, for the first plane, negative x plus 4y minus 2z equals 0, the normal vector is equal to negative 1, 4, negative 2. For 3x minus 12y plus 6z equals 1, the normal vector for that plane is 3, negative 12, 6. Now, if you notice, 3, negative 12, 6, which I called n2, is equal to negative 3 times the vector negative 1, 4, negative 2, which I called n1. So in other words, the vector n2 is equal to negative 3 times the vector n1. So what that tells me is that n2 is a scalar multiple of n1, and so therefore n1 is parallel to n2. And if the normal vectors are parallel, that tells me that the corresponding planes are parallel as well. And that's how we do 8a. Now, let's take a look at 8b. Suppose we are given the planes x plus 2y plus 2z equals 1 and 2x minus y plus 2z equals 1. Now, for the first plane, x plus 2y plus 2z equals 1, the normal vector n1 is equal to 1, 2, 2. For 2x minus y plus 2z equals 1, for that plane, the normal vector n2 is equal to 2, negative 1, 2. Are the planes perpendicular? Well, let's check that out. Now, we have the normal vectors n1 and n2. For n1, we have the vector, it's equal to 1, 2, 2. For n2, this one is equal to 2, negative 1, 2. To determine whether the normals are perpendicular, I take their dot product. And it turns out that the dot product of n1 and n2 is not equal to 0. Okay? And that tells me that n1 is not perpendicular to n2. And if the normal vectors are not perpendicular, then the planes can't be perpendicular either. Okay, so in other words, I want you guys to notice something. Let's draw a picture. Here's n1, right? Here's n2. Now, by design, if you guys can imagine, n1 is perpendicular to plane 1. So we'll say this is plane 1. Imagine this plane in 2 dimensions. N2 is perpendicular to plane 2. Okay? If we notice, if N1 is perpendicular to N2, that's going to force these planes to be perpendicular to each other. So in other words, they would intersect in 90 degrees. If N1 is not perpendicular to N2, there's no way those planes can be perpendicular to each other. So I hope that makes sense. Now, let's find the angle of intersection between the planes. Now, it's sufficient to find the angle of intersection between the normal vectors. Now, recall, cosine of theta is equal to n1 dotted with n2 divided by the length of n1 times the length of n2. But the dot product of n1 and n2 is equal to 4. The length of n1 is equal to 3. The length of n2 is equal to 3, so the denominator should be 3 times 3. But that says cosine of theta is equal to 4/9. And so theta is the inverse cosine of 4/9, which is approximately equal to 63.6 degrees. let's take a look at number 9. Find parametric equations for the line of intersection of the planes. Also find the angle between the planes. So we're going to look for the angle between the planes first. Now, the planes that we're going to look at are 3x minus 2y plus z equals 1 and 2x plus y minus 3z equals 3. For the first plane, 3x minus 2y plus z equals 1, n1 is equal to the vector 3, negative 2, 1. Okay? For the plane 2x plus y minus 3z equal 3, the normal vector n2 is equal to 2, 1, negative 3. Now remember, we're looking for the angle first, and then we'll find the line of intersection. So we need the dot product of n1 and n2, which I claim is going to equal 1. Okay? Now, the length of n1 and the length of n2 end up both being the square root of 14. Now, cosine of theta is n1 dotted with n2 divided by the length of n1 times the length of n2. So if I put everything together, cosine of theta ended up being 1 over 14, right? So theta is the inverse cosine of 1/14th, which ends up being approximately 85.9 degrees. And so what does that mean? The angle between the planes is approximately 85.9 degrees. So that's the first part of the question that I just answered. Now let's find the line of intersection. And come over here. To find the line of intersection, we're going to pick 2 points on the line of intersection. So first, I let z equal to 0, and I solved this system for x and y. And when I do, I get x equals 1 and y equals 1. And so p is equal to 1, 1, 0. So in other words, if I replace x with 1, y with 1, and z with 0 in both equations, that p will satisfy both of those equations. Now, I'm going to let z equal 1. And when I let z equal 1, I'm solving the system 3x minus 2y equals 0 and 2x plus y equals 6. And if you notice, when I solve the system, I get x equals 12 sevenths and y equals 18 sevenths. And so q is equal to the ordered triple 12 sevenths, 18 sevenths, 1. Now I got 2 points on the line of intersection, and that allows me to find the equation of that line. And that's what I do next. So here we have p equals the ordered triple 1, 1, 0, and q equals the ordered triple 12 sevenths, 18 sevenths, 1. And we form the vector pq. Remember, terminal minus initial, and so that vector will be 5 sevenths, 11 sevenths, 1. Okay? Now, we're trying to find parametric equations for the line. I start with the vector equation and then transition into the parametric equations. Now, I happen to choose, in this case, point P. Remember, we have the vector that runs parallel to the line we want, right? PQ is the vector that we want that's parallel to the line of intersection. And we just have to pick a point on the line. I happen to choose the point P, which is 1, 1, 0. So the vector XYZ is equal to the position vector of the point I chose, which in this case is 1, 1, 0, plus t times the vector that runs parallel to the line. So in other words, I'm going to take the vector 1, 1, 0 plus t times the vector 5 sevenths, 11 sevenths, 1, where t is a real number. Now, from here, it's much easier to transition into the parametric equations. So if you notice, my parametric equations are x equals 1 plus 5 sevenths t, y equals 1 plus 11 sevenths t, and z equals 0 plus 1t. Now, a question that might come up is, could I write z equals t? Of course, the answer is yes. And then t is a real number. Okay, these are my parametric equations. And that's how we do example 9. Now, the distance d from the point x1, y1, z1 to the plane ax plus by plus cz plus d equals 0 is given by capital D is the absolute value of ax1 plus by1 plus cz1 plus small d divided by the square root of a squared plus b squared plus c squared. Now, if you guys can imagine, suppose this is a plane. Pretend like that's a plane. And we have a point, which I'm calling x1, y1, z1. I want the distance from that point to the plane. And what that means is I want the perpendicular distance down. So in other words, I want this distance right here. Otherwise, there would be all kinds of answers. Okay, so this is the formula that gives us that distance. So we're going to call this capital D. And in another video, I actually prove this result. And I will upload that video as well. Okay, let's take a look at an example. Suppose I said find the distance between the given parallel planes. Now, I do want you to notice something. If we go back to this formula, notice how the plane is set to 0. That is crucial, okay? Because if you don't set it to 0, it's going to throw off what your value of small d is, and it'll also throw off what your distance would happen to be in reality. So we want to make sure any plane we're dealing with is set to 0. Okay. Now, with that said, we're finding the distance between the given parallel planes. Now, the first plane is 2x minus y plus c equals 4. Right away, I want to set this plane equal to 0. And when I do, I get 2x minus y plus c minus 4 equals 0. And then the other plane is 4x minus 6y plus 2z equal 3. Again, that plane is not set to 0. So over here, I set it to 0. So I have 4x minus 6y plus 2z minus 3 equals 0. Now, here's what I want to do. I have two parallel planes right here. We have plane 1 and plane 2. I'm going to pick a point on plane 1. And I'm going to find the distance from that point to the other plane. Okay? So I pick a point on 2x minus y plus c minus 4 equals 0. Now, could I have picked a point on the other plane? Absolutely. I claim it'll still work the same way. Now, I'm going to pick the point 0, 0, 4. Why? It's convenient. It's an easy point to deal with. So notice when x is 0 and y is 0, z is forced into being 4. And I want the distance from 0, 0, 4 to the other plane, which is 4x minus 6y plus 2z minus 3 equals 0. Now, That 4 is A. My negative 6 is B. C is 2. And D is negative 3. Okay? Now, this first coordinate here is x1. The second 0 here is y1. And this 4 here is z1. And it's just a matter of plugging stuff in. Remember, capital D is ax1 plus by1 plus cz1 plus d divided by the square root of a squared plus b squared plus c squared. And it's just a matter of plugging in. So I get 4, a is 4, x1 is 0, plus negative 6 times 0. Here, let's make a little room here. We'll do it below. So we get 4 times 0 plus negative 6 times 0 plus 2 times 4 minus 3, right? Divided by the square root of 4 squared plus negative 6 squared plus 2 squared. Now, that looks like 5 in the numerator, and in the denominator, we get 4 squared is 16, 2 squared is 4, 16 plus 4 is 20, and then negative 6 squared is 36, 20 plus 36 is 56. So we get the square root of 56, which is 5 divided by, and that's going to be 2 square root of 14. And that'll do it for this video for section 12.5. Again, this is a video based off the lecture notes. Thank you.